So now let's get down into the details, and what we need to do is we need to apply Coulomb's law to determine the force acting on Q2, the force acting on Q2 by Q1. We'll then repeat the application of Coulomb's law to determine the force acting on Q2 by Q3, and then we'll use the law of superposition to determine the total force acting on Q2. So just remember, Coulomb's law says that the force acting on point B from a charge located at point A is equal to QA, QB, 4 pi epsilon times R BA, the magnitude of it squared, A hat BA. Okay, general formulation of Coulomb's law. So that's what we need to apply in this situation. So the first thing we're going to do is we're going to determine the force acting on 2 from 1. So R12, the vector, is going to be the x components. Remember, this is the x-axis here. Nothing had an x component. There's 0 minus 0 a hat x. And then we've got 4 minus 0 a hat y. And we've got 0 minus 4 a hat z. So that's equal to 4 a hat y minus 4 a hat z. So that's this vector pointing from here to here. So that's the vector. The magnitude of R12 is equal to the square root of 4 squared plus minus 4 squared. So that's 16 plus 16 equals root 32, or 4 radical 2. The unit vector pointing from Q1 to Q2 is just this vector divided by the magnitude of the vector. So hopefully a lot of this is looking familiar to you from the last videos. So this is just 4 over 4 radical 2 a hat y minus 4 over 4 radical 2 a hat z. And we can see the 4's cancel out, so that's 1 over root 2 a hat y minus 1 over root 2 a hat z. That's the unit vector that points in this direction, so that's that little guy right there. And so now what we can do is we can determine, using Coulomb's law right there, the force on charge 2 from charge 1. So I'm going to just utilize some space and move over here. F12 is therefore equal to Q1, Q2, 4 pi epsilon, magnitude of the R12 vector squared, A hat 12, and that is equal to 10 nanocoulombs, 10 E, 10 times 10 to the minus 9 coulombs, times the charge here is 2 nanocoulombs, 2 times 10 to the minus 9 coulombs, over 4 pi epsilon. Epsilon is 8.854 times 10 to the minus 12 farads per meter. Normally we need to multiply by the relative permittivity. We're going to assume free space, so relative electric permittivity is just 1. We then need to multiply by the magnitude of R12 and square that, so that's times 4 root 2 quantity squared, and then we need to multiply by the unit vector pointing in the direction from 1 to 2, charge 1 to charge 2, and so that's all times 1 over radical 2 a hat y minus 1 over radical 2 a hat z. So there's Coulomb's law for F12. if we carry out this multiplication, we're going to end up with a two-dimensional vector quantity as our solution, and that is 4a hat y minus 4a hat z. This is a force. Forces are measured in nano. The actual result of this is that that's 4 times 10 to the minus 9th for both of those quantities. So I'm just going to put that they are in nanonewtons. So the force vector of charge 1 acting on charge 2 is 4a hat y minus 4a hat z nanonewtons. So now what we have to do is we have to determine the force acting on Q2 by Q3. It's a very similar procedure. So we start by determining the vector pointing from charge 3 to charge 2. And if we look at the locations, it's, again, neither of them have any x component to them, so we can just say it's 0 a hat x. The y component, this one has 4 units, this one has 0 units, so it's plus 4 minus 0 a hat y. And then when it comes to the z components, it is 0 minus negative 4, so 0 plus 4 a hat z, so it just gives us 4 a hat y plus 4 a hat z. The magnitude of that we can see is going to be the same as the magnitude of this guy, so the magnitude of R32, just by the property of symmetry that we see there, is 4 root 2. And a hat 32, we can pretty much tell that it's going to be the same unit vector, just instead of pointing in the negative z direction, it's going to point in the positive z direction. So it's 1 over root 2 a hat y plus 1 over root 2 a hat z. So I skipped a little math, but I think you guys probably get that. If I were then to apply Coulombs' law here to determine the force of particle 3 acting on particle 2, I'm going to get, because of the symmetry in this particular problem, I'm going to get 4 a hat y plus 4 a hat z nanonewtons. And I know I skipped a lot of steps, but it's exactly the same method as I showed above, so I don't want to waste either of our time. The next important step is that we have to apply the law of superposition to determine the total force. So total force is just F12 plus F32. So we just do vector addition. So we know that is going to be this vector here plus this vector here. So it is equal to 4 plus 4 a hat y plus minus 4 plus 4 a hat z, which is just equal to 8 a hat y nanonewtons is the total force acting on that. And so this is where I would stop and do my sanity check. My result is that all the forces acting solely in the y direction due to cancellation of the z components here. And indeed, that's what we predicted was going to happen originally. So that gives us a good way to just not validate the numbers so much, but to at least say, okay, well, that jives with what I thought was going to happen. So it's a good little check.